Good morning, students. Welcome to Complex Analysis live lectures. In this class, we'll define harmonic function and we'll see properties of harmonic function and how they are related with analytic function. Okay, so let's start with a definition of what is meant by a harmonic function. Harmonic function. So, a real valued function, a real valued function h in two variables x comma y, okay, uh, defined on a domain say D is said to be harmonic if the partial derivatives of this h, that means hx, hy, and first order as well as second order, if they are continuous, okay, and satisfies a Laplace equation which is hxx plus hyy equal to 0, then we say that it is harmonic function. So if first and second order partial derivatives of h are continuous and satisfies the equation which involves partial derivatives hxx plus hyy equal to 0, and this equation is called the Laplacian equation. Is definition clear? When we say that a real valued function h is said to be harmonic in a given domain, hello, so the first and second order partial derivatives should exist and they should be continuous, and the partial derivative should satisfy this equation hxx plus hyy. That means differentiate twice with respect to x and differentiate twice with respect to y, and when you sum them you should get 0. Okay, so let's take one example. The temperature function which you can denote by tx comma y, which is e power minus y into sin x, okay, is harmonic. This is harmonic in entire complex plane. Okay, so if we want to check that why this is true, clearly this is entire function. So clearly tx comma y is equal to e power minus y sin x is analytic, that means it's differentiable. Okay, now to check this tx, what is tx? That means partial derivative of t with respect to x, keep y as it is, e power minus y. For sin x it is cos x, okay, this implies, and t one more time if you do, then it is minus e power minus y sin x, okay, and what is ty? That means keeping sin x as it is, this is minus e power minus y times sin x, and therefore tyy one more time if you do, then you will get e power minus y sin x, minus of minus again plus, right? So therefore txx plus tyy is 0. Okay, and this function e power minus y into sin x is harmonic function. Okay, that means partial derivatives exist and satisfy this condition. Okay, any problem? Hmm? Okay. Now we'll see how this we can give lot of examples using this analytic functions. That means we by the following result we can have a number of analytic these harmonic functions. Namely, if a function is analytic, then its imaginary and real part are harmonic functions. Okay, that means if f of z, which is equal to ux comma y plus I vx comma y, is analytic, say in a domain in D, then ux comma y and vx comma y are harmonic. So whenever we know an analytic function, if a function is analytic, then its real and imaginary parts are harmonic functions. Okay, harmonic functions, right? So proof is not at all difficult one. What is given that this f of z, which is equal to ux comma y plus I times vx comma y, is analytic. Okay, so if this is analytic, then we know by definition it is differentiable. Okay, so therefore the partial derivatives exist. Okay, and they are continuous. If we want to show that this u and v, they are harmonic functions, what we want to show, that uxx plus uyy equal to 0. Similarly, vxx plus vyy equal to 0. Right? Okay. So here we use one result which we prove later, that if a function is analytic, then it is infinitely differentiable. Okay, that means it is differentiable of given any order and they are obviously continuous. Okay, that means we will prove this later. This implies, because it is analytic, if all partial derivatives of all orders, implies partial derivatives of all orders exist and are continuous. Okay, this we will prove later in coming sections. That means when we discuss more about analytic functions, at that time we'll show that if f is analytic, then its derivative exists whatever order, all orders. Okay. Fine. Now also f is analytic, therefore in particular CR equation satisfies, right? Since f is analytic, CR equations hold, are satisfied in this and the domain D. Okay, this implies ux is equal to vy and vx is equal to minus uy. Clear? Any problem? This implies if we want to differentiate this, you want to get uxx, right? So if we differentiate this one more time, what we will get, uxx is equal to vyx. Okay, and this vx. Okay, and you differentiate this with respect to, okay, you first we will do it for u, so this we will differentiate with respect to y. That means this is vxy is equal to minus uy. That means what we are doing here, this we are differentiating with respect to y, and here we are differentiating this with respect to x. This implies uxx plus uyy is equal to, this is vyx and minus vxy. Okay, now what is this vxy and vxy? First you differentiate with respect to x and you differentiate with respect to y, because Partial derivatives of all orders exist and are continuous. Therefore, this order we can interchange. That means it is whether you first differentiate with respect to x, then y, or with respect to y first, then x, both are same. Okay. That means since f is analytic, okay, we have this vyx is same as vxy. So therefore uxx plus uyy is equal to 0. Same way you can do it similarly. What we get is vxx plus vyy is equal to 0. That means here whatever we are having this CR equations, the first one you differentiate with respect to y, and here you differentiate with respect to x. Then again using the you can interchange this differentiation order, and you will get vxx plus vyy equal to 0. So what this result says is that if we know that some function is analytic in a given domain, then its imaginary and real and imaginary parts are harmonic functions. So if we take some example to understand, example, so suppose let f of z, take f of z is I upon z square. What can you say about this function? Whether this function is analytic, if at all it is analytic, where it is analytic? Hmm? Where is the problem for this function? Hmm? The problem is that z is equal to 0, right? Other than that, it is a rational function. We know it is analytic. Yes or no? So therefore, this function is analytic in a domain, or analytic at all points, non-zero points, right? Then we know that f of z is analytic for all z not equal to 0. So if you take any domain which does not contain 0, then f of z is analytic on that domain, right? Yes or no? Now if we know this real part and imaginary part, then those two are harmonic functions, right? So how you can simplify this? F of z I times z 1 by z square. In numerator you have to make it so this you didn't multiply and divide by z bar square, right? Yes or no? This is x minus iy whole square. That means we are converting this into ux comma y plus iv v of x comma y. This is mod z over 4, right? Z into z bar is mod z square, right? So what we have here is this. Is this clear? Because it is z into z bar whole square, but z into z bar is mod z square, so you will have whole square. Okay, if you want you can write like that also, there is no problem. So you want you write this then here. Okay, this is same as I into x square, okay, minus y square minus 2 I xy upon mod z square is x square plus y square, then you have this. Okay, that means mod, if I simplify this further, what you have here is minus of I into I, which is I square, so this is 2xy, okay, plus I times, this is 2xy by x square plus y square whole square plus I times x square minus y square by x square plus y square whole square. Is that clear? This is our f of z, which is ux comma y. This implies ux comma y, which is equal to 2xy upon x square plus y square whole square, and vx comma y, which is x square minus y square. If there are any calculations missing, Okay, you just point out they are harmonic functions. Clear? Hmm? Right? So if you given any function, if we know that is analytic, then so these are harmonic functions on domain a domain not containing origin, right? Because this one is not analytic at 0, so therefore this domain, whatever domain we are taking, that domain should not contain origin. Clear? Hmm? Huh. Where? Where? But I is there, right? I square value is what? Hmm. Huh. A minus b, if you take it, this is like a b, then a minus b whole square is a square plus b square minus 2ab, right? Hmm? Any problem? Hmm? Clear. Okay. Fine. Okay. Now we'll define what is something called harmonic conjugate. Okay. Then we'll see how they are related with analytic function. Okay. So we say that a function, you take two real valued functions u and v. Okay. If their first and second order partial derivatives exist and are continuous, and if they satisfies CR equations, then we say that v is harmonic conjugate of u. Okay. So we'll write first that definition. If u x comma y and v x comma y are harmonic functions, are harmonic functions in a given domain D, okay, and satisfies, okay, and yeah, and satisfies means before that satisfies, and their first order partial derivatives satisfies CR equations, okay, of course throughout D, then then we say that then we say that V is harmonic conjugate of U. So when we, this conjugate is nothing to do with Z bar, what we usually define. This word is used in different sense. Okay. So when we say that V is a harmonic conjugate of U, both should be harmonic functions and they should satisfy CR equation. Okay. Is that clear? Hmm? So that means what is meaning of this? This U and V are harmonic, okay, and satisfies this ux is equal to vy and vx is equal to minus uy. If this property is satisfied, then we say that v is harmonic conjugate of u. Okay, fine. Uh, Here u need not be harmonic conjugate of v. Okay, even though this u and v you can interchange, but we will prove a result now. From that, it is not necessary that if u is a harmonic conjugate of v or v is harmonic conjugate of u, then u need not be harmonic conjugate of v. Okay, is that clear what I am saying? From this definition, it from this definition you can interchange u and v. Okay, that means either you say v is harmonic conjugate of u, or u is harmonic conjugate of v, but not both. Is that clear? Hmm? That we'll see in this following result. Means we prove a small result, but which is useful to understand what is this harmonic conjugate. Okay, so we can give relation between harmonic conjugate and an analytic real part and imaginary part of analytic function. A function f, you can write f of z is equal to ux comma y plus I times vx comma y is analytic if and only if v is harmonic conjugate of u. Okay, so this, whenever you have a analytic function, then we can definitely say that v is a harmonic conjugate of u. Is statement clear? For example, we have seen here this f of z is equal to I upon z square. Okay, it is analytic throughout the domain not containing 0, right? So therefore this v, whatever we are having, x square minus y square upon x square plus y square whole square, this is harmonic conjugate of u. Okay, proof is not a difficult one. It is actually follows everything what we know already. Suppose that f of z is analytic. Okay, then we want to show that this v is a harmonic conjugate of u. By definition, they u and v should be harmonic functions. Okay, and they should satisfy CR equations, right? But we already proved a result that if your function is analytic, then u and v are harmonic functions. Is that clear? This implies u and v are harmonic by previous theorem. Whatever we have discussed, we know they are harmonic. Also, because f of z is analytic, it is in particular differentiable at every point in that domain, right? So therefore they satisfy CR equations in that domain, right? Yes or no? Also, f of z is analytic implies this CR equations hold in that domain, whatever domain we have defined, right? Is that clear? This implies V is a harmonic conjugate of U, right? Now take conversely. So conversely, suppose V is a harmonic conjugate of U. By definition, we know that by definition of harmonic conjugate, this implies U and V are harmonic functions, right? Yes or no? So if u and v are harmonic, by previous theorem which we have proved is that f of z, which is equal to u plus iv, is analytic, right? So this result is actually consequence of the previous result, only writing in different words. That means proof, right? Is that clear? Hmm? Ha. Now, as I said, before this result, we'll write as a remark. So the remark is that if V is a harmonic conjugate of U, that U is harmonic conjugate of V is not necessarily true. Okay. Then U need not be a harmonic conjugate of V. Is question clear? Huh? What we are saying? If one is the harmonic conjugate of the, if V is harmonic conjugate of U, it is not always true that U is harmonic conjugate of V, right? Hmm? For example, you take U which is equal to x square plus y square, okay, and uh, V is equal to say 2xy, okay. Then then f of z which is equal to u x comma y plus I times v x comma y which is equal to x square plus y square plus 2i xy, okay. uh, what is this will become, huh? x x plus iy whole square, no, that x plus iy whole square if we take, okay, so we want to take here, you take x square minus y square, okay, this you take it as x square minus y square, then this will become x plus iy whole square, x square minus y square plus 2xy. Is this clear? Which is same as mod z square, not mod z square, it is same as simply z square, right? Yes or no? Hmm? So we know that f of z is equal to z square is analytic, right? This is analytic, right? Yes or no? It is a polynomial, so therefore it is analytic everywhere. It is actually entire function. So because this is analytic, by this previous result, what we can say? V is a harmonic conjugate of U. Yes or no? Huh? This implies Vx comma y, which is 2xy, is a harmonic conjugate of this U, which is x square minus y square. Whereas if we want to show that U is a harmonic conjugate of V, our new function is what? Hmm? Whereas whereas you can call it some capital F of Z, which is instead of u plus iv, what you will have now is v plus iv, which is v plus iu, 2xy plus I times x square minus y square is, okay, not analytic. Why this is not analytic? Can somebody see? Hmm? If we want to show that this function is not analytic, let's find out what are CR equations for this. Hmm? For this, if you call it this as capital U x comma y, which is 2xy, and v x comma y is x square minus y square. Then what is CR equations? That means this ux is 2y, right? Yes or no? And uy is 2x. What is similarly vx is 2x and vy is minus 2y, right? Clear? Any problem? So can ux equal to vy? Huh? What what are your equations? Ux is equal to vy and vx is equal to minus uy, right? Yes or no? So can vx is equal to uy and ux is equal to vy? Huh? From this, what you will get? Ux is equal to vy and vx is equal to minus uy implies you get that x comma y is equal to 0 comma 0. Is that clear? Only possibility is 0 comma 0, right? Any problem? This much is clear, right? If ux is equal to vy, then y has to be 0. Similarly, vx is equal to minus uy, then x has to be 0. Okay? So this is differentiable only at one point, namely 0 comma 0. Therefore, it is not at all analytic at any point. Yes or no? So therefore, this whatever x square minus y square, right? This if v is a harmonic, what we have written, if u f of z is equal to ux comma y plus I times vx comma y, then we say that v is harmonic conjugate of u. So therefore, here this is not analytic because this is not analytic. So this is since, okay, this is not analytic function. Therefore, x square minus y square. This implies x square minus y square, which is you call it as capital U, okay, is not harmonic conjugate of, right, of v, which is 2x1. Clear? Hmm? So if u is a harmonic, or if v is a harmonic conjugate of u, then it is not necessary that u is also a harmonic conjugate of v. Okay, actually you can take one exercise. When this is true, if you try, if you are not getting, I'll explain. Okay, when it will be true is only fact that if u is a harmonic conjugate of v and v is a harmonic conjugate of u, then u and v should be constant. At only at that point it is possible. So what you can write this as exercise, so that if v is harmonic conjugate, if v is harmonic conjugate of u in domain D, and u is a harmonic conjugate of v in the same domain, okay, then u and v must be, then ux comma y and vx comma y must be constant, throughout D. Okay, this is one. You can try. If you are not get, I will give solution or how you can prove next class. Simply use the fact that, what you will get, whatever result we have proved earlier, you just start using that fact. Okay, fine. Now we'll give one method how we can find, given an harmonic function, how we can find its harmonic conjugate. Okay, so we will give example. We'll show through an example how we can find a, given a harmonic function, how we can find another function which is its harmonic conjugate. Okay, so find a harmonic conjugate find a harmonic conjugate of ux comma y, which is let me take one example, which is y cube minus 3x square y. Okay. How we will find? Hmm? We'll assume that Vx comma y is a harmonic conjugate. Then whatever properties it satisfies, from that we will find Vx comma y. Okay. So let Vx comma y be a harmonic conjugate of this given function u. Right? Yes or no? Then what we know by previous result? This result, if V is a harmonic conjugate of U, then what we know? This F, which is Ux comma Y plus I times Vx comma Y, is analytic. Yes or no? This implies Ux comma Y plus I times Vx comma Y, okay, is analytic, right? So therefore, in particular, the CR equations are satisfied in this domain or not? Hmm? This implies is analytic, say on some domain D, right? This implies the CR equations must fall on this entire D. That means what we know, Ux is equal to Vy and Vx is equal to minus Uy at every point in this domain. Is that clear? Hmm? U is given to us, and which therefore we can find Vy and Vx, right? Yes or no? This implies Vy is equal to Ux. That means you have to differentiate partially with respect to x. That is nothing but what is Ux from here? Huh? Y cubed will be there when you are differentiating with respect to x, keeping y constant. Huh? What is this will become? Minus 6x. Huh? Y is there, right? Here y will be there because it is a multiplication, right? Partial derivatives also I have to teach now. This is ux, which is nothing but minus 6xy. Is that clear? Hmm? Huh. And and vx is equal to minus uy, which is this we have to differentiate with respect to y, keeping x as fixed. So this is 3y square. Yes or no? Hmm? 3y square minus 3x square. Any problem? Hmm? 3y square. This is 3y square minus 3x square. Which if you want, you write it as 3x square minus 3y square. Is this clear? Now, there are two ways. You fix x and integrate this with respect to y. Okay, you will get vx comma y. Or this you integrate with fixing y, you integrate with respect to x, you will get vx comma y. Is this clear? Hmm? Anyone you can use it. Either you differentiate this, integrate with respect to, if we integrate with respect to x or with respect to y, depending on which function you are selecting. Is that clear? Hmm? Suppose you take 1. If we want to take 1, we want to get v. So we want to integrate with respect to what? Because it is the differentiation with respect to y. So we want to integrate with respect to y. Is this clear? Hmm? Integrating 1 with respect to y by keeping x fixed. we get, what we'll get? V of x comma y. Okay, that means we are integrating this with respect to y. What we will get? What is the integration of this function minus 6xy with respect to y? Hmm? Huh? Minus 3x y square, because y square by 2, 2 and this 6, 3 you will get, right? Yes or no? But is this only, or you will have something plus some constant or plus something? Hmm? Because when you are integrating, you will have some constant, right? Yes or no? Plus some c. Yes or no? But remember, this x, whenever you change some x, you will get some different constant. You will change x, you will get some different constant. Yes or no? That means whatever this constant we are getting, it is actually depending on x. Hmm? That means whatever we are going to write here, it varies based on what x we are taking. So that I will denote by phi x. Okay. So where this phi x, why we are getting? Huh? Huh. So you have to understand, if this x, for example, here 6x naught y is there, then this might be simply some c naught. Okay. Is that clear? Because this x you can vary, whenever you vary this x, you will get different constant here. That's why this phi we are denoting simply that by phi x, and we will find that phi, what is phi x. Okay. Hmm? Is a function, because for every x we get a constant, you can call it cx, we get a value cx, right? That we are denoting simply as phi x. Clear? Hmm? Now take this as 3. How we can find this phi x? Can we relate this now with second equation? Hmm? We know exactly what is Vx, and here we have V function V, but it involves an unknown. We want to find that phi x. So what we can do is 3. We can differentiate this 3 with respect to x, keeping y fixed. Yes or no? Hmm? Hello. See, we want to find somehow this, what is this phi of x? We cannot have u just like that. We should know what is this exactly, right? Even though it is a function in x, we should know exactly what is this value. For that, we have another information. For this Vx, we have exact value, which is 3x square minus 3y square. So therefore, this equation 3, we can integrate, we can differentiate with respect to x by keeping y fixed. Huh? So differentiate 3 with respect to what? X. We get Vx, which is equal to minus 3y square. Yes or no? Plus phi dash of x. Any problem? Hmm? Is that clear? So this is supposed to be Vx, and we already have an exact value for Vx. So if we use 2 and 4, if you call it this is 4, then by 2 and 4 we have, huh? Because this is equal to this, so Vx is 3x square minus 3x square minus 3y square is equal to, which is again minus 3y square plus phi dash of x. So minus 3y square will get cancelled, and phi dash of x is equal to 3x square, right? So therefore, how you will get phi of x? Huh? How will get phi of x? Now integrating this one, you will get phi of x is x cube. Now you will get some constant here. Yes or no? Hmm? Earlier this one we have two variables y and x. So therefore that constant whatever we are getting is depending on x. But this is directly one constant. Are you following? Hmm? Therefore, what is Vx comma y is, if you substitute in 3 minus 3xy square plus x cube plus some constant, right? Any problem? Therefore, this is a harmonic conjugate of the function, given function u. So how we do? What is the simple procedure? Take, suppose v is a harmonic conjugate of u, then we know obviously u plus iv, which is a function, is analytic, so it satisfies CR equations. Then from 1 vy, you integrate with y, then whatever you get v, that you differentiate x and equate, you will get phi of x. Yes or no? Hmm? Have you understood? So if you have understood, you write down these exercise problems and solve so that you are comfortable. Okay. So show that ux comma y is harmonic in some domain D, in some domain, and find a harmonic conjugate vx comma y for the following: ux comma y is 2x into 1 minus y. This you note down and you solve the problem. Okay, ux comma y is 2x minus x cube plus 3x y square, and third one is ux comma y is equal to sine hx hyperbolic function sine y, and ux comma y is y upon x square plus y square. Okay, this is one. And you can also have some interesting example to show that if, say, suppose u and v, suppose v, if small v and capital V suppose are two harmonic conjugates of if of the function u, then of course on a given domain D whatever, okay, then this small v and capital V, they differ by an additive constant. Okay, then this v and capital V, okay, can differ by differ at most by an additive constant. What is meaning of saying this? Can somebody tell? Hmm? What is the meaning of saying that they differ by at most an additive constant? Hmm? Hmm. That means either v is some v plus some constant. Okay. Yes or no? Hmm? That means they cannot be two different functions. Maximum there will be a, just like see here, if you observe in this problem, we have some c here, right? Yes or no? Hmm? You can easily check that even this one is also a, you can check that minus 3xy square plus x cube, or you add some more constant, that is also a harmonic conjugate of u. Okay, because this constant doesn't change the results. Okay, so if you have two harmonic functions, then they should differ by a additive constant. Okay, so if you forget about, that means if you consider this, forget about this additive constant, then they are same. Is that clear? Yes or no? Also, let's see whether any other examples or interesting exercise is there, because somebody asked some give more exercise, so I will keep giving more exercise. Of course, whoever interested, you solve, and if you are not getting, you are most welcome to ask. We will discuss. uh, show that show that V is a harmonic conjugate. V is a harmonic conjugate of U, of course, in a domain D. Okay, if and only if, say in D, if and only if minus U is a harmonic conjugate of V in the same domain. Okay, so what we remark, if V is a harmonic conjugate of U, then U need not be a harmonic conjugate of V, but minus U is always a harmonic conjugate of V. Okay, is this clear? Hmm? Yes or no? That means if you take V is a harmonic conjugate of U, we want to show that minus U is a harmonic conjugate of V in D, right? So what is the hint here? Can somebody tell how you can write in terms of analytic function? Hmm? V is a harmonic conjugate of U is if and only if U plus IV. Yes or no? Hmm? This is analytic. We want to show that this is analytic if and only if minus U is a harmonic conjugate of V means what? Hmm? If you write this as capital F of Z, how you can write this? Is same as, huh? No, V plus, hmm, this minus U, I times minus U is, just a second, is analytic. If we prove this, we are done. Yes or no? Hmm? Solve this problem, and if you have any difficulty, you can ask me in next class. Okay, we'll stop here and we'll see in next class.